Okay. Well, good afternoon again, everybody. My name is Christina Medved. I'm the Director of Community Outreach for the Roaring Fork Conservancy, and we are really excited to have you all here today. We have people here from all over the state of Colorado and beyond. So I wanted to go ahead and just welcome everybody, give you a little bit of background on who the Roaring Fork Conservancy is before I turn the microphone over to Dr. Diane McKnight, who we are really excited to have here with us today. So I'm going to ask everybody to go ahead and please mute yourselves. And then I'll discuss in a few minutes here how we are going to go ahead and handle questions today. So just as a really brief introduction to Roaring Fork Conservancy, we are located on the western slope of Colorado. This little blue area here is our watershed in the area that we work in. And we might seem like a small watershed. We're only about 1,400 square miles. We are roughly the size of the state of Rhode Island, but we are actually a very important watershed and for the entire Colorado River Basin. And that's primarily because surrounding our watershed divide here are 7 14ers that can hold on to snow well into spring and summer on those really good years and can contribute a lot of flow to the Colorado River. So we are actually in our 25th year as the watershed organization for the Roaring Fork Valley, and our mission is to inspire people to explore, value, and protect the Roaring Fork watershed. And we primarily fulfill our mission through our watershed science and policy programs and our watershed education programs. So our watershed science includes everything from targeted studies to stream monitoring. In our policy work, we engage with all stakeholders to come up with solutions to improve our streams and our rivers. And in our watershed education programs, we teach over 5,000 individuals a year through our K through college programming and also our family and adult programming. And I invite you to go to our website to learn a lot more information about our programs. And so just a brief introduction to our watershed, just to give you a little bit of background here. The orange colors here are the really high elevations, and then this like very light green color down here are river valleys. So the Roaring Fork River begins here where this blue pin is near Independence Pass. It flows through the city of Aspen and then through Basalt, which is where we are located, where there's a confluence with the Frying Pan River. Once we're back in the Roaring Fork River, we head down to Carbondale, where we have the confluence with the Crystal River. Crystal River flows 40 miles before it reaches the Roaring Fork River. And then ultimately the Roaring Fork River will flow into the Colorado River. Now, the best that we have with our mapping tools here, with all of the curves and the twists and the turns in the Roaring Fork River, the Roaring Fork River flows about 75 miles before it gets to Glenwood Springs. And while, as I mentioned before, we might be a small watershed, we contribute about 10% of the total flow to the Colorado River watershed. And in addition to being known for our gold medal fishing rivers, our hot springs, our ski slopes, we're also home to one of the most photographed mountain ranges in North America, the Maroon Bells, which is just down the road from us here. Now, I mentioned our three major rivers because our three major rivers begin in designated designated wilderness areas. And here, our wilderness areas are fully forested. And so we actually have really good water quality here. Now, at some point during this presentation, we are going to be talking about the samples that were collected at Alpine lakes here in the watershed. And those are located here near the headwaters. They included Lincoln's Lake, Independence Lake, and Lost Man Lake. So it was in 2019 that we started the Brookshire Watershed Institute, and that was primarily in response to us wanting to engage the public and at a higher level scientifically, if you will, and to invite water leaders locally, regionally, nationally, and even internationally to talk about their water expertise and to share it with us. Now, Diane, we found Diane last summer. It was just a little bit of a miracle that we found you when we did, Diane, so thank you. Karen Teague from the Independence Pass Foundation, who is on this call, sent us an email, I think it was last August, and said, hey, Christina, we're seeing a lot of algae in the lakes up high, we're talking 11, 12, 13,000 feet. And so we were able to mobilize our water quality team to actually go and collect some samples of that algae, but not before we found Diane and her team and started asking a lot of questions like, what is happening here? Is this something that was on our radar? but this is something that Diane has been studying for a lot of years. So we're really excited to have you here. I'm going to stop the screen share here, Diane, so that you can go ahead and get yourself situated. And while she's doing that, I would love to introduce you to our friend, Diane McKnight. So Dr. McKnight began her career with the U.S. Geological Survey and is now a distinguished professor in the Department of Civil, Environmental, and Architectural Engineering and a fellow of the Institute of Arctic and Alpine Research at the University of Colorado. Her research focuses on the coupling of hydrology, aquatic ecology, and water quality. She studies streams, lakes, and wetlands in diverse regions, including acid mine drainage, streams, and alpine lakes in the Rocky Mountains, polar desert streams in Antarctica, and wetlands in Botswana and Bangladesh. She has been president of the American Society of Limnology and Oceanography, editor of the Journal of Geophysical Research, Biogeosciences, and has served on numerous committees for the National Research Council. She is a member of the National Academy of Engineering and is currently chair of the executive board of the Long-Term Ecological Research Network. So we are so excited to have you, Diane. Thank you so much for taking the time to be here with us today. For those of you that will have questions throughout the presentation, please leave them in the chat box, which I will be monitoring, and I'll go ahead and interrupt Dan with any of those questions. So on that note, I'm going to turn the microphone to you, Diane.
Well, thank you very much, Christina, and it's a real pleasure to be here and to be sharing with you some of our research. And as Christina emphasized, I'm a professor, so I'm very interested in trying to explain processes, and I'll try to emphasize that and not so much talk about a lot of data slides for this presentation. And I will not actually be presenting the data from the Roaring Fork Alpine lakes, but giving you a context from lakes that we've studied in the Rocky Mountains. And our research is based on what we call an ecosystem framework, and lakes were really the motivation for first thinking about how ecosystems work. And here's a little cartoon for introducing this idea that a lake is a microcosm. So that helps us understand phenomena that's relevant to understanding all ecosystems. And here's a picture of Bear Lake, Rocky Mountain National Park. So you can kind of think of this lake as a microcosm. And another big idea in ecology, in 1935, Tansley proposed this idea that ecosystems are a fundamental unit of nature along a continuum from atoms to galaxies. So next time you visit a beautiful lake in the Maroon Bells, think of, here you are looking at a fundamental unit of nature. And so what's happening here in this framework of thinking about how climate change is making or altering how lake ecosystems function. Many of you have heard the phrase that there's actually two seasons in the Colorado Rocky Mountains, winter and road construction. Well, we have, if we think about it, these lakes in the high elevations are ice covered most of the time. So I've added this ice cover to our cartoon, October through June, that's 9 months. Here's a picture of Bear Lake in winter. And then it's July through September when the lake is ice-free. What's actually happening as a result of climate change is that this period of winter is decreasing and the period of summer is increasing. You know, in general, the duration of ice cover for alpine lakes in the Rocky Mountains has decreased 2 to 3 weeks. So if we think about that period, this is expanding the duration of summer. And I'll be showing you some data from the Green Lakes Valley in here in the Front Range of Colorado. Here's a picture of Green Lake 4, and here's a little map. And this data results I'll be showing you are from a paper by Diane Preston, who's now at Colorado State University, published in Geophysical Research Letters, and our team here at CU are co-authors on this study. And here is a graph showing ice-off date in days from April 1st and going from 1980 to 2015 for these different lakes in that previous map. Here's Lake Albion, which is actually a water source for water supply for the city of Boulder. And you can see that it doesn't take much to understand that these ice-off dates have been getting earlier relative to April 1st as a starting point. So the other point in this foundational paper in 2016 is a lot of other properties of the lake change with ice-off date. And so we want to think about how does that work? And I want to draw your attention to this last figure here. So this is ice-off date, days from April 1st on this axis and here on the vertical axis is chlorophyll A. So chlorophyll A is a measure of how much algae are present in the summer in these lakes. And what you can see is when there's 130 days between April 1st and when the ice goes off, the chlorophyll concentrations are lower than when there's only 70 days. And I hope that makes sense. And then there's a lot of other parameters that are changing: total dissolved nitrogen, total dissolved phosphorus, the dissolved organic carbon concentrations. You know, some of these don't have any strong trends, but the sulfate concentration does and the chloride concentration does. So we want to be thinking about the drivers for these trends in terms of both ice off, but also in terms of the water quality. So with that, I'd like to get back to this ecosystem framework. Another concept that was proposed based on this idea of an ecosystem as a fundamental unit of nature was this idea of trophic dynamics concept. A young limnologist, Lindemann, in 1953, put this idea forward. A limnologist is someone who studies lakes and streams. It's like a freshwater oceanographer. So here's our picture of Bear Lake, and here's a cartoon representing the different processes that are happening within the lake, within this microcosm. And I want to bring your attention to this box here, which is the phytoplankton. Again, chlorophyll is in the water is a measure of what's the biomass of the algae in the lake. And this cartoon is focused on this dissolved organic carbon box. Actually, most of the organic carbon, especially in an alpine lake, like Bear Lake, will be dissolved in the water as a constituent that adds a little bit of color to the water. In the case of an alpine lake, not that much, but that's really important pool of how organic matter is cycled in a lake ecosystem. So I've added this sun up here to indicate that the sunlight is very important in driving the growth of phytoplankton. And this is an important consideration in the context of this duration of ice cover shrinking. So here's another picture showing lots of phytoplankton. This in a lake like Bear Lake wouldn't be as abundant, but phytoplankton are microscopic plants, algae of different kinds. As you can see in terms of their characteristics here, this is showing a lot of diatoms, which have silica cell walls. And one point I'd like to make in terms of talking about phytoplankton in lakes is their is there a lot of diversity present in lakes? Is there a question? So here's on this left axis is a list of major types of algae. We have diatoms, which have these silica cell walls. We have green algae. Cyanobacteria are actually not eukaryotic organisms. They're bacteria, prokaryotic, dinoflagellates, chrysophytes, and cryptophytes. So there's a lot of diversity, especially compared to streams. So what this means is changes in how this lake functions can change which type of algae are present in the lake. So one way in which alpine lakes are changing is that the seasonal temperature changes are becoming more similar to the patterns that occur in lakes at lower elevations. And I'm going to try to explain this clearly. So in the summertime, in a lake here in Boulder, Colorado, we would have a situation where the surface water is warmer than the bottom water. And that's illustrated in this temperature graph here, where we would have maybe 28 degrees C and then 4 degrees C, cold water at the bottom. So the sunlight heats up the top layer, and that now there's no mixing between the top and the bottom. As winter comes on, as shown here, the surface water cools, and eventually there's a uniform temperature profile, and the whole lake turns over. So there's mixing from top to bottom that occurs. And then in the wintertime, we have ice cover. And so there's actually a lower temperature underneath the ice than at the bottom of the lake. And when the ice goes off, again, there's another time when the water temperature is the same from top to bottom and the whole lake mixes. Wind can actually drive mixing once we start approaching this time in March, for example. And then the lake between March and April will gradually, the surface waters warm up and stratify again. So this is a typical pattern in temperate lakes from New Hampshire to Colorado here on the plains. How were alpine lakes different? Well, in alpine environments, the air temperature at night is pretty cold, generally pretty cold. And so that prevented the surface water from warming up enough for the lake to stratify. And so this step just wasn't occurring, and that was more likely, especially with the high winds, for the alpine lakes to be mixed from top to bottom and not stratify in a thermally. And when this thermal stratification happens, that changes the chemistry of the lake. But now that it's warmer in the summers, many alpine lakes are beginning to stratify in summer, and that can change which types of algae are abundant. So that's an important point. Moving along, we can think, going back to this diagram, what's happening in winter is pretty important in this context. And carbon and nutrient cycling under winter ice cover is an important aspect of how alpine lakes function. So obviously there's less light, there's much less ultraviolet light, and so there's less growth of phytoplankton. There's also much less input of runoff from the surrounding landscape because it's all under snow and sort of frozen. And then there's an accumulation of dissolved gases. So when the phytoplankton grow, they take up CO2 and produce oxygen. So there can actually be higher concentrations of dissolved oxygen under the ice cover than would be the case if the environment, if the lake water was in equilibrium with the atmosphere. So we have no gas exchange, much less sunshine, and no runoff coming in. And whatever source of solutes or interactions that occur with the sediments, those become pretty important. So this is why this difference between open water and ice cover makes a difference. I would like to point out that very little is known about how these lakes work in the winter. As you can imagine, it's not easy to sample a lake through the ice cover in winter. We were very fortunate. Garrett Rue, who was a PhD student, collaborated with, worked with Rocky Mountain National Park to conduct a study of what was happening in Bear Lake in the winter. I don't know if any of you've been to Bear Lake. There's a parking lot nearby, so that allows access. And here is a graph showing that there are indeed changes in the phytoplankton that occur under the ice cover at different depths in Bear Lake through the winter, where we're going from February again to April. And these different colors represent these different groups of algae that I pointed out earlier. And the gray here is Dinoflagellate, a gymnodinium species that is capable of growing not only with a little bit of light, but also using some of the organic substrates that may be dissolved in the water, this dissolved organic carbon that I mentioned before. So they get a little bit of light that comes through the ice cover and get some more energy from this dissolved organic carbon that may be a carryover from the growth of the algae in the summer. So that's an important aspect of how this system works. Now, as I mentioned, alpine lakes are typically not that productive. And one way to think about this range of productivity in lakes is these three words. I'm going to try to limit the amount of the number of big words to use here. So oligotrophic means low productivity, mesotrophic, and then eutrophic is lots of productivity. And most likely some of you have seen green scummy lakes out on the plains sometime. So this is almost like the Goldilocks range, where we have not much algae, some algae, and lots of algae. And there's a very simple way that we can characterize the trophic status. This was an approach developed decades ago, and it's called a Secchi disk depth, where we have a plate, as shown here, and it's got this defined pattern, and you can be out in a boat and lower this Secchi disk from the side of your boat, and when you can't see it anymore, that's the Secchi disk depth. So if we have an oligotrophic environment like this, the Secchi disk depth may be several meters. But if there's a lot of growth of phytoplankton, it may be only a meter or less. So this is a very simple method that's still being used by limnologists, even though we have all these high-tech sensors that may be reporting other data all the time. It's a very simple way to characterize what's going on. So here's another definition of oligotrophic, and here's a picture of Maroon Lake, which is a classic oligotrophic lake. Low productivity due to low nutrient content. And the waters of these lakes are clear due to the limited growth of algae, and they are of high drinking water quality. And I'll be talking about that a little later on in this talk. And these lakes support species of algae and zooplankton and fish who require well-oxygenated cold waters, so especially lake trout. And these oligotrophic lakes are usually found in cold regions. They're not restricted to alpine and subalpine lakes.
Diane, I'm so sorry to interrupt. We had a quick question for you.
Sure.
From Patrick Hunter, he's asking what the role of zooplankton is.
So that is a very good question. I'm going back to my cartoon here. Well, obviously as shown, I shouldn't say obviously, but as shown in this diagram here, the zooplankton eat the phytoplankton, and then the zooplankton are food supply for the fish. So that's an important aspect of the trophic dynamics. So these zooplankton can be Daphnia, which are water fleas, and some of the zooplankton in alpine lakes have a high degree of protective pigmentation to protect them from the UV light that can be the radiance of UV that makes it through the water column. And I mentioned this dissolved organic carbon pool. This colored organic carbon functions like sunscreen in a lake because it particularly absorbs the UV light. Now, is that a good, okay answer?
I think so.
Okay, thank you.
That was great, thank you.
Yeah, so we'll go back. And so I'm going to talk to you about this idea of oligotrophic, mesotrophic, hypereutrophic. And in general, these oligotrophic lakes have very low concentrations of chlorophyll A. So the Bear Lake in the winter is in this range of 1 to 2 micrograms per liter. So you have to filter a lot of water to get a fair amount of algae. The nutrient concentrations are also very low in this. For phosphorus, it's between 4 and 7 micrograms per liter. And typically the nitrogen is also low. And here's the transparency in terms of meters. The Secchi disk depth that I mentioned, can be up to 12 meters in a very oligotrophic lake. So this allows us to put our alpine lakes and subalpine lakes here in Colorado in context. Now we want to think about, well, what else besides sunlight drives the growth of phytoplankton? And this is where it gets to this needing to think about the ratios, the amount of nitrogen and phosphorus. And so I'm going to introduce a fairly fundamental idea, and I hope it's not too daunting. So carbon and nitrogen and phosphorus occur in the biomass or the tissues of all these different kinds of algae. So I'm going to scroll back. Actually, I showed you, here's all these different kinds of algae, a lot of diversity. However, this ratio of nitrogen to phosphorus in the tissues of those algae are about the same. 16 to 1 on a molar basis. So if the ratio of nitrogen to phosphorus that's dissolved in the water or is coming in from the watershed is less than this 16 to 1, then that nitrogen is constraining, the availability of nitrogen constrains how much algae or phytoplankton there can be. Similarly, if the ratio is greater than 20, where there's more nitrogen than phosphorus, then the phosphorus availability or how much phosphorus there is can be limiting. And then if this ratio is somewhere in between, we have this idea of co-limitation. So algae need light, just like running a greenhouse, but they also need nitrogen and phosphorus. and to create biomass. Let me go back. So how does this work in a lake like Maroon Lake? One of the important sources of phosphorus back into the water column can be the release of phosphorus absorbed onto the sediments. If you remember the cartoon about the sediments, that goes back into the lake during the winter period. So here's, we have different forms of phosphorus. We can have dissolved inorganic phosphorus, and then it can be taken up by the algae and it goes into this particulate organic phosphorus. So the algae are a reservoir of phosphorus, and sometimes in an oligotrophic lake, almost all the phosphorus that's in the water column in the lake is in the algae. And then there's the algae die that may release some of the phosphorus, or as the algae are growing, they also release some of the phosphorus. And we get these different forms: dissolved organic phosphorus, dissolved inorganic phosphorus, and then bacteria take it up. So we have this phosphorus cycle going on in the water column, but it can really be driven by the release of iron oxide from the dissolution of iron oxides in the sediment, which can happen in the winter. So that this winter period is important in the context of the phosphorus availability. Is that helpful? Are there any questions in the chat about that? Oh, the other point I wanted to make is the phosphorus that comes into a lake may come from natural weathering of apatite and other minerals in the landscape during spring runoff, for example.
Now, I think we do have a question. April, do you have a question, April? Yeah.
Hey, Diane, thanks. I am getting lost in the chemistry. So if you can take a minute to remind me what it is that you're telling us, and then go back to how you're telling us. Does that make sense? Like,
yeah, okay. So
and then come back to the middle.
So let me go back. So one of the things that's changing, in addition to climate change, is the nitrogen cycle is changing, both globally and locally. And I'm going to
the
get
nitrogen cycle is changing not because of climate change; it's changing because of something else.
I'm going to explain this now and then get back. I started with phosphorus because phosphorus is simpler. But
oh god!
So when we here in the Front Range, we have nitrogen sources atmospherically from feedlots, from NOx emitted by automobiles. There's nitrogen in wastewater runoff. There's nitrogen applied on fertilizers. We humans have dramatically changed the nitrogen cycle, both locally and globally, by a factor of 2. Okay, so the nitrogen cycle has changed independent of climate change. I mean, maybe there's
human caused.
So there's, but you, in terms of understanding the impact on an alpine lake of the nitrogen cycle changing, we have to think about the phosphorus.
Okay.
Does that help?
Yeah, I just wanted it reframed so that I could.
Yeah, I'm reframing. I appreciate your question because as I said, I'm trying to start emphasize explaining things, and if I'm losing people, it's hard to tell with Zoom. So reframing this, we need phosphorus, and there is some internal cycling of phosphorus in a lake, year to year. So going back to my little diagram here, there's phosphorus that gets released from the bottom of these sediments back into the water column on an annual seasonal basis. Okay, so then the algae, for algae to take up phosphorus, they don't take it up, they don't take up particles, they take up dissolved forms, like dissolved like a salt, just like sodium chloride dissolves in. You put a teaspoon of salt in your water glass, it will dissolve. So the algae like to take up dissolved inorganic phosphorus. And then, so that's what assimilation is into their biomass. And then that produces another phrase here is POP, particulate organic phosphorus. Another way of thinking about that is phosphorus in algae. And there's also phosphorus in zooplankton and such. And then that's being turned over as well. It doesn't just get taken up and never gets back to the dissolved pool again. So we have this cycling of phosphorus going on in the lake. And often it's hard to measure this because these forms of the dissolved inorganic phosphorus are very low. They may be undetectable in an alpine lake. Okay, so are we ready to go to nitrogen? So nitrogen, one reason it's complicated is because there's not just one chemical form of nitrogen. There's 7 redox states of nitrogen. So I'm just going to show you this really quickly. It's complicated. And I don't want to try to go through this, but there's different redox states of nitrogen. So ammonia is at the same redox state of the nitrogen that's in the biomass in the algae. But then the nitrate that comes, say, is deposited on snowpack from the oxidation in the atmosphere of NOx's emitted by car exhaust is at the other end of this nitrogen cycle. So when we say it's complicated with reference to nitrogen, it's really true. It's not just the scientists being obscure. And the other issue is some of these gaseous phases, nitrogen, N2 gas, that's mostly in our atmosphere, but N2O is a greenhouse gas, for example. So I wanted to, give you that perspective going back here to understanding how this changes in these nitrogen to phosphorus ratios may be changing which types of algae are dominant and which ones we might be concerned about. So when we want to sample, understand the phytoplankton in a lake and its productivity, this is why we always want to know something about how much nitrogen and phosphorus is there. And then moving along, I wanted to end on a more upbeat note by talking about this dissolved organic matter that the algae can produce. So we have the dissolved organic matter that runs off from the landscape into the lakes, and then this dissolved organic matter that can actually be produced by the algae that are growing in the lakes. So this is one area of potential regulatory influence for thinking about addressing these issues, because dissolved organic matter is when water is treated with chlorine to disinfect water to make it drinkable, we can have this production of disinfection byproducts that can be considered potentially hazardous, carcinogenic, tetragenic. And so the Environmental Protection Agency has regulations about what the DOC concentrations can be in a water supply if in order to chlorinate the water. And so if the DOC concentrations increase too much, then the water needs to be treated to remove that DOC before the water can be chlorinated. And this can allow us to try to constrain some of the nutrient inputs into lakes, because the Safe Drinking Water Act can be called into play. So here's the chlorophyll concentrations shown here. And here is the DOC concentrations. And this was data from a study of 30 lakes across the state of Colorado and run by the Colorado Department of Public Health and Environment. And we can see that the high range of DOC concentrations are ones where this chlorophyll A concentration is much higher. So this is the range down here of our alpine lakes. And as we go to more and more chlorophyll A, the DOC concentrations in summer go up. And the threshold where we need to think about removing this DOC before chlorinating the water is actually at between 2 and 4 milligrams carbon per liter. So, and the Colorado Department of Public Health and Environment back in 2012 proposed some optional or advisory regulations to protect high quality water supplies, which certainly applies in the Roaring Fork based on nutrients and chlorophyll A concentrations. And this was not acknowledged as a proactive climate change action. And it's within the scope of the environmental regulations, especially the Safe Drinking Water Act. So with that, I want to, this is a more expansive slide. There's a lot of science going on nationally, but we have the capability here within Colorado and within our own watersheds to proactively understand what's going on and implement regulations within the federal regulatory framework. So I didn't want to leave you with this kind of discouraging perspective. There's not that much we can do about these global climate trends causing warmer, longer summers, but there are pathways to proactively manage nutrients. So with that, I'm done.
All right, thank you, Diane. We have about 15 minutes for some questions, and we do have a couple, but I'm going to go ahead and just add to what your presentation is, Diane. We were learning a lot of this with you and through reading some of your journal articles and some of the articles of your former students that we found and were researching last summer. And so we do, as I mentioned earlier, we did send samples to Diane, and her lab was able to identify what we were finding in the 3 alpine lakes that we sampled. And so we do have a preliminary report of what those findings are. It's a little too much for us to get into right now to give it the time that it should have. But if you're interested in that, just send me an email and I'll get you in touch with Chad Rudo, who's our water quality program manager, and he can give you some more information on those results, because I know we have a few people here that I think that would be interested in that. In addition, we're going to continue sampling those lakes and potentially other lakes. So anybody on the call here that really loves to hike up high, that you maybe love to fish in some of our alpine lakes, or you just love to go where there are no people, we might be interested in talking to you in the future, because there is coming a point where we're not ready for it yet, but we might be recruiting volunteers that, hey, I'm going on a hike anyway this Saturday. Can I collect some samples for you? Which we would say yes, but we would need to train you how to do that. Diane has agreed for her and her lab to continue helping us, but we need to pay for that because this is somebody's time and expertise. You could imagine that there are not very many labs in the world that do the work that her and her team do. So if anyone knows of good funding sources for us to approach for some of this work, we would really appreciate that, because like I said, this is new on our radar. So on that note, I just wanted to throw that all out there, but I'm going to go ahead and jump into these questions, Dan, because they're starting to come in. So okay. So, and if there's anything else you want to add, Diane, to that as well.
No, as I said, we weren't quite ready to put the data that we received, that we generated in this first report, into this broader context. So I thought we'd start here, and getting some algal samples is good, but it would also be great to get some nitrogen and phosphorus.
Exactly.
Yes.
So we will be continuing this conversation.
Yeah.
Okay, so let's go with Elizabeth. Thanks for patiently waiting. Her question was, is the algae that we're seeing in these lakes, is it toxic? Is it taking the oxygen away from the lakes? And is it affecting native fish in the lakes?
Okay, well, there are several questions there. I'm going to go back to this previous diagram here. So say if there's more phytoplankton growing than the zooplankton consume, some of this phytoplankton biomass will settle down to the bottom of the lake. And then when there's ice cover, that organic matter is degraded. And so that can reduce the amount of oxygen in the bottom of the lake in the wintertime. You know, it can be, so that can be deleterious to the fish because these lake trout require cold, highly oxygenated environments to live. So that's one issue of having more phytoplankton in the summer can carry over to be problems in the winter. Once the lake ice does form and there's no more oxygen getting into the lake. I hope that makes sense. And then with respect to the types of algae, I'm going to go back to this graph here, this figure here. The two types of algae that can produce these toxins that you may have heard about are cyanobacteria and sometimes the dinoflagellates. Dinoflagellates or chrysophytes. But in terms of these cyanotoxins, those can be a problem if there's a particular strain of cyanobacteria that takes off, and that would typically happen in the late summer, early fall. So that's one reason that this later ice on can allow conditions where these cyanobacteria can become abundant. It's a big question, what are the environmental conditions that would drive a population of cyanobacteria that's just doesn't have any toxin in it in the biomass to becoming dominated by strains of those algae that have toxins. That's an important research question. You know, here in the Boulder area, we are collaborating with Boulder County Open Space and Mountain Parks on studies to try to understand that here. But just because the water is a little green doesn't mean it's a toxic situation.
Great. Okay.
And one more clarification, you may have heard of this Didymosphenia or Didymo or rock snot. That is a diatom that's in streams and it's never toxic.
Thank you for clarifying that, Diane.
Yeah.
Okay, I'm going to try to get through as many of these questions as we can before you have to go. A question from Scott is, what is the source of nitrogen at lakes at 12,000 plus feet?
So there can be nitrogen deposition onto the snowpack. And then when the snowpack melts, all that nitrogen comes into the lake. And so some of this nitrogen deposition can be actually emitted from power plants to the west of Colorado and brought atmospherically. Here in the Front Range, some of the nitrogen deposition on the snowpack comes from upslope winds from Denver and Boulder and Greeley onto the snowpack. And then there's a lot of internal cycling of the nitrogen in the lake.
Okay. I don't know if it was April or George, but that raised your hand first. So I'll just go to George since it's where you're located on my screen. I see your hand up, and then we'll go to April's question. Oh, George, we can't hear you. If you need to unmute, please.
Can you hear me now?
Yes.
Okay. Just a couple comments. Most lakes of the world are phosphorus limited, not nitrogen limited. The lake that I managed was phosphorus limited, basically because the watershed was so small and the lake so large, water volume and size. So our atmospheric loading was doing about half of the phosphorus loading, which left us as a manager to deal with the phosphorus coming from the land, as opposed to the Alpine lakes, which is all nitrogen limited, and it's all air movement, so there's virtually no management, I would think. It's problematic. The other thing is, you just never know. We had a very mesotrophic lake, but in the last 20 years, the Secchi disc said it's somewhere uber oligotrophic to oligotrophic. The reason being is the zebra mussels have come in, and they've sucked out all the algae in the water column, excepting for the blue greens. So yet we're still mesotrophic. So those are my comments.
Well, thank you very much, George. And I meant to say another common word for cyanobacteria are blue-green algae. You may have heard that. And that they actually look a little bluish when you look in a lake where they're really abundant. And yes, the zebra mussels have changed a lot of cycling in lakes. Yes. April or whoever should go next.
Yeah, let's go with that question, and then we have another couple minutes for us to close up.
Thank you, Diane, so much for that information. Is what's happening in the high alpine lakes that we're seeing in the Roaring Fork, is it unexpected? And is it happening in all of the high alpine lakes in Colorado?
Well, we can't say whether it's happening in all of the alpine lakes in Colorado because very few alpine lakes in Colorado are monitored, are studied, or sampled. You can't know what's happening if you don't measure it.
More directly, what I'm asking is there something unique in the Roaring Fork watershed, or would you expect that if it's happening in the Roaring Fork, it's probably happening in Colorado?
It's probably happening all throughout Colorado because some of what's happening has to do with the physics of the situation and the fact that the summer nighttime temperatures are not as cold as they used to be. And that is happening across the state, but in the Colorado Rocky Mountains. But as George said, it matters. The details of the lake itself matters.
Mm-hmm.
Yes.
And then are there regulations that can help? Are they water quality regulations or are they air quality regulations?
Well, certainly air quality regulations can help in terms of nitrogen deposition. But the point I was making, if there's local sources of nutrients, the regulations through the Safe Drinking Water Act on dissolved organic carbon concentrations, if a water body is used for water supply, can be useful. And for that to happen, there needs to be a study of what the dissolved organic carbon concentrations are, how much of these disinfection byproducts are being produced, when that water is chlorinated. But there are regulatory pathways.
But that's useful in helping ensure that we have safe drinking water. What is useful in helping to ensure that we preserve and protect the aquatic life in these lakes?
Well, those would go hand in hand.
Okay.
Is my point.
Okay.
Potentially.
Okay.
I'm not saying that they will, or this is relevant to Roaring Fork or whatever, but so I'm going to tell a story if you don't mind. So we published this paper in Limnology and Oceanography about dissolved organic carbon. And there's a prominent journal, and we had a complicated model that considered this lake mixing and how much organic material was released in solution from this much chlorophyll. And we thought, oh, you could have a model that would do this predictively. And then the next year, the Colorado Department of Public Health and Environment got in touch with my colleagues here in environmental engineering And they said, we're going to do an empirical study of 30 lakes and we're going to figure it out. And as I said, by 2012, 3 years later, there was something on the table being considered by the Colorado Water Quality Commission. So this isn't just pie in the sky. Okay?
Thank you, Diane, and thank you everybody for your questions. I know there's a few more questions that we did not get to. I just took screenshots of them and I will email them to Diane if you have some time to get back to us later this week. That would be really great. But I did, before we close out today, I first of all want to thank you again, Dan. We really appreciate you sharing your many years of research and expertise with us and seeing so many different scenarios. One of the reasons that we are interested in continuing to monitor this in our alpine lakes is because of something Dan said earlier. There's not a lot of alpine lakes being monitored. And as we're getting less precipitation and we're getting warmer temperatures and warmer water, at least down here in the river valleys, especially in the summertime, our rivers are getting warmer, our dissolved oxygen levels are getting lower, and it's stressing aquatic fish. Well, one of the things we can do is we tell people to go up high to go fish because it's cooler up there. And it is cooler up there, but what we don't know is, because we haven't been studying it, at least here, is it still warmer up there than it should be, even by 4 degrees or 3 degrees? And is that enough to cause some different ecosystems changes? And that's why we want to continue studying this. So I'll wrap that up to invite you all to join us next Tuesday for our final Berkshire Watershed Institute of this winter season, which is with Dr. Francisco Zamora with the Sonoran Institute. He's going to discuss what they've been doing to restore the delta in the Colorado River. It's really, really amazing work that they're doing down there with just a little bit of water in the river. They've been doing some amazing things. That presentation will be at 6 o'clock in the evening. And then I don't have time to pull up my PowerPoint here, but on March 12th, we are going to be leading a program with NRCS to McClure Pass so that you can tour a snowtell site. I don't know if you guys can see that. You can get the information on our website, and maybe I'll follow up with you all also with an email. And then, we are a nonprofit. We do love providing these education programs to you all, but we do ask you to consider to potentially becoming a monthly base flows member, as we call it, which is someone that would maybe on a monthly basis make a donation to us for the work that we do, or you can even make a one-time donation. We would love to have you become a friend of our organization. So Dan, thank you again. We're hard stop at 12:30 for you to go to your next meeting. And if anyone has any more questions, please get in touch with me and I'm happy to pass them along to Diane.
I really appreciate the opportunity to talk to you all. Bye.
Thanks, everybody. Bye-bye.